Hello and welcome. This video is a continuation to the previous video in which we introduced Laplace transforms. So today we are going to be looking at the Laplace transforms of elementary functions. However, before we can start looking at that, I would like to remind ourselves about a way in which we can think of Laplace transforms, because everything that we'll do from this point will be basically based on the way in which we can think about Laplace transforms. So a Laplace transform in the nutshell is basically taking a function and performing some operations on that function, and then obtaining another function, which is in this case a Laplace transform of the function we started with. So yeah, that's how we can think about Laplace transforms. So with that in mind, I think we can get started with today's work. So the Laplace transforms of elementary functions that we'll be looking at are functions such as f of t is equals to 1, f of t is equals to k. So k is just a constant, just a number, 1, 2, 3, and so on and so forth. And f of t is equals to e to the power a t, and f of t is equals to cos at, and so many more. So we'll look at more functions as we proceed. So given a function, so f of t is equals to 1, we can perform the Laplace transform of that function simply by putting a 1 where there's f of t in the definition of the Laplace transform. So as you can see, this right here is the definition of the Laplace transform, and f of t is the function that we are performing the Laplace transform on, and so we put that function where f of t is. So in this case, the function is simply a 1. So as you can see, where there's f of t, we simply put a 1. Yeah, so if we put a 1 where there's f of t, the function simply becomes an integral of the number e to the power s, which is a parameter of real values, I believe. So we simply have e to the power minus st with respect to t. So we are basically integrating between the boundaries of an infinitely large number and 0. So when we integrate this, we simply take the differentiation of the power. In this case, the power is minus st. So the differentiation becomes, of course, with respect to t. So if we differentiate that, we get minus s, and we put it as the denominator of the integral after we perform the integration operation. So we get the function we had started with, and we put the differentiation of the power as the denominator and the function as the numerator, and of course without forgetting the limits there, which we can then separate. So we put the infinitely large number where the t is, and also we subtract that. We get the same, and we subtract the same, but in this case we put 0 where there is t. So yeah, basically we simply, in this step, what we are simply doing is we are factorizing 1 minus 1 over s from this function, and so we simply remain with e to the power minus st, which we can now distribute the boundaries, and we have that. So the infinitely large number goes here and the 0 goes on the other one. So we can think of this as e is a number, and this is s is a number, and this is a very large number. When you multiply this, you get an even bigger number, but you have a negative index, which means reciprocal. So the bigger this product gets, the smaller the entire number gets, and you basically end up with a 0 at some point. So that's how we end up with this. And finally, the Laplace transform of this function, which is simply a 1, is 1 over s. So so the key takeaway from what we've just said here is that whenever you are taking the Laplace transform of this function, which is in this case f of t is equals to 1, its Laplace transform is 1 over s. And that's the thing that you need to always remember from what we've just talked about. Yeah. Then we can also look at the function f of t is equals to k. So what we've basically done is, where there was a 1, we've multiplied it by k. And remember what we had said in the previous video when we looked at the linearity properties of Laplace transforms. So when you have a constant, and when you are multiplying a function with a constant, you can basically push the constant out of the Laplace transform, and yeah, that's what you end up with. And you recognize this part here as the Laplace transform of the function f of t is equals to 1. And yeah, so you can just simply plug the Laplace transform of this function here, and you end up with the Laplace transform of f of t is equals to k, being k over s. So therefore the Laplace transform of a constant is equals to the constant over